Spanning tree is a protocol that is designed to block and stop loops on a layer 2 network. Loops on a layer 2 network is bad because that can result in broadcast storms, which can bring down an entire network in a matter of seconds. So spanning tree is recommended to be enabled on all layer 2 devices, whether VLANs are used or not. So this picture here kind of reflects many different loops that can exist. Like this here is a loop, or this here is a loop. So there are a lot of loops here, especially when you're dealing with fully mesh switching topologies, just like this. Spanning tree has three main modes of operation for how it operates with other layer 2 switches connected on the network. First, it will determine the root bridge, which is done for each VLAN that is added onto the layer 2 network. Second, a single root port is determined for each of the other switches. And third, the designated port and non-designated ports are determined for all remaining segments within the topology. Let's go through an example of this, and we will use this topology here. So here we have 4 switches all meshed together. Hence, there are several loops established. You will see in this picture the MAC address and the priority value of each switch reflected right here. And you'll see that the default priority is 32.768, but the MAC address for each switch will be different. You will also see that for each connection between these switches here, you will see a cost value, and the cost for each of these segments will be 10. Now this cost is determined based on the bandwidth media of the connection. So in general, higher the bandwidth speed, lower the cost value. So with this diagram, let's show the spanning tree operation. Also keep in mind that all of this happens automatically by spanning tree. There's nothing that you are specifying. You can for some parts, but all of this operation happens automatically by the operation of spanning tree. Now this process occurs for each VLAN that is used on the network. But let's assume that this topology has a single VLAN. So the first process is to determine the root bridge in the topology. Well, only a single switch within this topology will be chosen to be the root bridge based on its bridge identifier, or BID. And the bridge identifier is based on the priority and the MAC address of that device. That makes up the bridge identifier. So the switch with the lowest priority would be the root bridge. Well, in our case, the default priority is used on all of these switches, 32.768. Therefore, the switch with the lowest MAC address will be chosen for the root bridge. So in our case, that will be switch 1. So that will be the root bridge for this particular environment. The next step is to determine the root port for all of the other switches except for the root bridge switch. That means that we need to determine the root port for switch 2, 3, and 4, not the root bridge. Let's start with switch number 2, right over here. So the root port would be a single port on this switch that has the shortest path based on the cost to the root bridge switch. Well, there are several paths from switch 2 that it can take up to the root bridge. One path is directly connected right here, and the total path cost to that root bridge would be 10. Well, another path could be going through switch 3 and then up to the root bridge. Well, that would travel across 2 interfaces, this interface here and that. So that means that the path cost would be 10 plus 10, which means it would be 20 to reach the root bridge across this particular path. And there's another possible path that it could go to switch 4 and then once again up to the root bridge. And that will have a total path cost of once again 20, 10 plus 10 being 20. Therefore, there are many other combinations, like even from here, 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 and there. But the shortest path from switch 2 to the root bridge would be this port right here. Therefore, this would be the root port for switch number 2. And we can determine the same thing for the other switches, and that will basically be the interfaces that are directly connected to the root bridge itself. So on switch 3, it will be this port here. That will be the root port, which is directly connected. And for switch 4, it will be this will be the root port, which is directly connected up to the root bridge. The last step is to determine the designated ports and non-designated ports for all segments that we haven't marked yet in this topology. So by default, all ports on the root bridge would be designated ports. These are basically interfaces that are connected to the root ports on the other switches. So doing that, we are left with 3 segments. We have the segment here, here, and here that we need to determine which one is the designated port and which one is the non-designated port. Let's focus on the segment that is between switch 2 and switch 4, this connection right here. So one of these ports between these switches will be the designated port and the other will be a non-designated port. So the designated port would be the switch with the lowest bridge identifier. So in our case, that will be switch 2. So switch 2 has the lower MAC address compared to what switch 4 has, which means that this would be the designated port and the other end by default would be the non-designated port that we see here. We can do the same for the other segments, the segment here and the segment here, to determine the designated ports and the non-designated port. So for example, between switch 2 and switch 3, which one has the lower bridge identifier based on the MAC address? Well, that would be switch 2. This is a lower MAC address compared to this for switch 3. Therefore, this will be the designated port and this will become the non-designated port. And that will complete the span tree process, and this will determine which ports are forwarding and what will be blocked ports. So all of the designated ports will be forwarding, which you'll see here. They're all considered as forwarding ports. And all non-designated ports will be blocking, which is reflected here, here, and here. Now this means that they will be logically blocked. The ports themselves will not be actually disabled or shut down. So in this particular topology now, we know what is being forwarded and we know what is being blocked. Therefore, if there is a client, like a computer for example, that is connected to switch 4 right here, and it wants to connect to a server that is connected off of switch 2. Therefore, the flow of traffic will go from switch 4 through the forwarding port up to the root bridge switch, and then over this connection here to switch 2. So these are the 3 main ports that we talked about that are basically determined within the span tree topology. We have a root port, the designated port, and the non-designated port. These are also determined and is part of the rapid span tree protocol as well. Well, if rapid span tree is enabled, there are 2 additional port types that are used. There is the alternate port, which is simply a backup root port on the switch. And there is a backup port, and that is basically a backup designated port on the switch. This means that if the root port or designated port on a switch goes down, then the alternate or the backup port would become active ports right away, depending on what port actually went down. And this will result in a very fast convergence, which we'll talk about in the next few slides coming up. But this is one of the main advantages for why it becomes rapid span tree if this is enabled on the switches. In our environment, based on our design, this is how we will be configuring span tree based on data center best practices among our switches. So all of our switches will be enabled for rapid span tree as a best practice. In terms of the root bridge location, it will exist within our core layer, but it will be distributed based on the VLANs. So DC1 will be the root bridge for all even numbered production VLANs, including any other VLANs that are used. That will be VLANs 10, 12, and 999, our bit bucket native VLAN. DC2 will be the root bridge for all odd numbered production VLANs, which would be 11 and 13. So doing this will force different forwarding and blocking ports, making all of our interfaces available for data traffic. So these are the details for how we will be configuring and testing span tree within our data center environment. Let's start our span tree configuration on the network. The great thing about this step is that span tree is already enabled by default and running the rapid span tree protocol. This can be confirmed by using the command show spanning tree. Okay, and here you will see that span tree is enabled and using the rapid span tree protocol. Remember, span tree applies for each VLAN. So for VLAN 1 and here's VLAN 10, you will see that span tree is enabled and of course running the STP protocol, the rapid span tree protocol. But we want to make some changes to span tree within our topology based on best practices. Starting on DCC1, we first want to enable the path calls to be long and not short, which is the default. So doing this change will cause the span tree protocol to use 32-bit values when determining the port path calls compared to the default 16-bit value. Now this is recommended because the data center networks will likely consist of 10, 40 to even 100 gig connections, and the path calls won't change that much. Hence, how the path is determined may not be ideal. So this provides expanding the range of the port calls if higher speed links are used in the environment. Next, we want to force DCC1 to be the primary root bridge for all even numbered VLANs on our network, including the native VLAN. To do that, we'll go ahead and type in spanning tree, VLAN, 10, 12, and our native VLAN. And next, we will specify a low priority value. Now the default priority is 32,768. So we're going to use a low value for this. Now keep in mind that if the system ID has been extended, which is important if you want to use up to 4,000 VLANs, then the default priority would change. So in the case of like VLAN 1, for example, what you do is that you would add 1 to the default priority, which will actually be 32,769, which you see right here. That 1 pertains to the actual VLAN tag ID, which will be VLAN 1. So just keep that in mind. That's why down here for VLAN 10, since the system ID has been extended right here, it basically will be 32,768 plus 10, and of course that will be that number for the priority. But again, we want DCC1 to be the primary root bridge, and doing so, we need to use a low priority value that we talked about earlier during the concepts and further in our design section. Okay, so moving along, we will also make DCC1 the secondary root bridge for the odd numbered VLANs. And to do that, we will use a priority value that is basically between the default and 4096. So let's go ahead and specify spanning tree, VLAN. We will list the odd numbered VLANs, which would be 11 and 13, and priority, and again, a number in between the default and 4096. We'll say something like, there we go. Next, let's go to DC2, right up here. And there, let's set the path calls to be long. Path calls method long. Okay, next, this switch will be the primary root bridge for the odd numbered VLANs. So that will be 11 and 13. Okay, and it will be the secondary root bridge for the even numbered VLANs, including the native VLAN. Okay, so doing that, we are doing the reverse of what we did on the primary core switch. In terms of our access switches, they will not be the root bridge for any VLAN. However, as a best practice, we will enable the path calls to be long, starting with DCA1. Oops, spanning tree, path calls, method, long. And let's do the same on DCA2. Let's set the path calls to be long. We are finished with our span tree changes. For confirmation of what we did, let's go back to DC1. And there, let's view the span tree domain for VLAN 10. Okay, so we know that we should be the root bridge for all even numbered VLANs. And for VLAN 10, we do see that DC1 is indeed the root bridge within our data center topology, which is reflected right here. This bridge is the root. You'll also notice that the priority is set to 4106. Well, why is that? So the extended system ID is 10, which is based on the VLAN tag, and that has been added to the priority value. Therefore, that sum in total will be 4106. You basically add 10 to the priority that we manually set before, which is 4096. For the section right here that says root ID, this information right here is about the actual root bridge in the topology. Well, that will be this switch, as it says right here, that this bridge is the root. We also see the priority value right here and the MAC address of the root bridge for VLAN 10. And as you can see, it matches what exists for the bridge ID. The priority is the same, and even the MAC address itself is the same. So the bridge ID section is information about this local switch, which is again the root bridge. Now, when we go to DCA1, go to that switch, and if we run the same command, you will see that this information will be different for the root ID and for the bridge ID. At the bottom here, you will see which interfaces belong to VLAN 10, and that will be our layer 2 port channel, which are enabled as trunking ports. Now, since DCC1 is our root bridge, all ports will be designated forwarding ports, which you see right here. Designated is the row, and forwarding state. You'll also see that the path calls for those interfaces is reflected as 1000. Now let's view the span tree domain for VLAN 11, and we know that DCC2 should be the primary root bridge for all odd numbered VLANs like 11 and 13. So once more, under the root ID section right here, you will see that we are not the root bridge this time. Instead, we see information on who is the root bridge for VLAN 11. We see the priority value, which is reflected right here, and the MAC address of the root bridge, and this belongs to DCC2. For the bridge ID section, this pertains to this switch, DC1. And there you will see our priority isn't lower. This is our priority right here, that it is not lower compared to what is set up on DCC2. And the priority is based on the value that we set plus the VLAN tag ID, which is 11. So you add those up, and that will give you the number that you see here, and even for this as well. Now, since we are not the root bridge, one of the interfaces that exists in VLAN 11 will be the root port, and that will be reflected as right here, port channel 12, which is directly connected over to DCC2, and that makes sense because that is the shortest path. And the other ports are in the designated forwarding state. So once again, our root port is port channel 12, which is of course in the forwarding state. And the other interfaces based on the span tree process is in a designated, they're designated ports, which means that they are also in a forwarding state. Let's view the span tree domain for VLAN 10, but on DCA1 this time. Let's go and type in, let's exit out here and do show spanning tree VLAN 10. Oops. Okay, and once more under the root ID right there, you will see the details of DCC1, which is the root bridge for VLAN 10 based on the MAC address that we see here and the priority that we saw earlier. Under the bridge ID, we see the span tree details for this local switch. the default priority, and of course the MAC address on this switch. And at the bottom here, you will see that the root port is port channel 13, which is directly connected to DC1. And port channel 23 right here is the backup root port called the alternate port. And of course, that is currently in a blocking state. The other interface, basically which connects directly to the server, is in a forwarding state. It is active, which makes sense because we want that server to communicate with other devices on our data center infrastructure. Now, let's view the span tree domain for VLAN 11, which should look a little different. So let's go back up and do 11 this time. Okay, so here you will see that the root bridge is pointing to DCC2. This is based on the root ID information, looking at the MAC address, and of course looking at the priority. This is details that we saw earlier for that device. And of course we see our own bridge ID information, the same details. Now for the root port, it is different. The root port is port channel 23. That's the root port, which is directly connected up to DC2. And the backup root port will be port channel 13, which is the alternate port, currently in a blocking state. Let's cover some other commands for monitoring span tree. On DC1, let's enter the command show spanning tree root. And this command will show a summary of all of the root bridge switches that exist for each VLAN, a nice summary. So here we see our production VLANs, including the default VLAN, which is VLAN 1, the first one right up here at the top. So we know that this switch is the root bridge for all of the even numbered VLANs. That would be 10 and 12. Therefore, in this list, we do see them listed and that we are the root bridge for those VLANs. So VLAN 10, this bridge is root, and for VLAN 12, this bridge is the root bridge. And of course, the other production VLANs, which is 11 and 13, DC2 is the root bridge for those VLANs, and that is reflected based on showing which port is the actual root port on that switch. So that will be port channel 12, which is correct. Another command which we used before is show interface trunk. And here, let's go down towards the bottom a little bit, go down a little bit more. Okay, and here you will see details, this section right up here, you will see details of the switch ports that are in a forwarding state based on the span tree operation. Now, let's go to DCA1, for example, and let's view the root bridge list. Okay, so there we see everything that we expect to see for this switch. We see that the root ports for VLANs 10 and 12 are port channel 13, which connects up to DC1. And we see that the root ports for VLANs 11 and 13 is port channel 23, which connects up to DC2. But we also see that this switch, our active switch, is the root bridge for VLAN 1. Yikes, we don't want to make any active switch the root bridge. It should be on the core or distribution layer. So we will make those changes shortly to follow best practices. As a result, when we use the command show interface trunk, and let's go down a little bit, right here, that is why we see VLAN 1 listed for both port channels under span tree forwarding, because all ports on a root bridge are in a designated forwarding state for each VLAN. So in this case, for VLAN 1, DCA1 is our root bridge, and that means that all of those ports will be forwarding. You will also see that port channel 13 right here is active and forwarding for the even numbered VLANs, which is 10 and 12. And you'll see that port channel 23 is active and forwarding for the odd numbered VLANs, which is 11 and 13. So those ports are the root ports for that specific VLAN. So this command can provide some of those useful details. Okay, so let's make DC1 the root bridge for VLAN 1. Now it is an odd number VLAN like 999, but that rule only applies for our production VLANs. So VLAN 1 and 999, they are not production VLANs used by our servers. So let's go back to DC1 and let's make this switch the root bridge for VLAN 1. Say VLAN, 1 priority and our low priority. Okay, great. Now let's view the span tree domain for VLAN 1. Okay, and there you will see that we are the root bridge for VLAN 1 and that all ports that are in VLAN 1 are in a forwarding state. Therefore, let's go back to DCA1 and let's view the root bridge list again. Okay, and now we see that DCA1 is no longer the root bridge. We see that the root port for VLAN 1 is port channel 13, which is connected up to DC1 as expected. Now, before we continue on, let's do a failover test to make sure that our two servers can continue to communicate with each other. So right now we have server 1 connected off of DCA1, and we know server 2 is connected off of DCA2. So when server 1 wants to communicate with server 2, we know that it'll be traveling along a particular path based on our span tree configuration that we just completed. So what is that path as a recap? So what happens is that from DCA1, from server 1, it will go up through port channel 13 to DC1, down port channel 14, down to DCA2, and then on to server 2. Now what we would do is create a failure on port channel 13, and that should then do a reconvergence because of span and tree forcing a different path very quickly. So that new path from server 1 will go to DCA1. It will go over port channel 23 up to DC2, and then down port channel 24 down to DCA2 and then to server 2. So on server 1, let's do a continuous ping to server 2. It's a 10.0.0.2. Okay, that's running. Let's go ahead and move this aside. From DCC1, let's view the ARP table. Do a show IP ARP. And there we see one entry for server 2's IP address mapped to its MAC address because of the ping tests that we are running. Now that server's MAC address ends in 4121. So let's remember that for later. Now let's go to DCA1. Let's go to that tab. And here, let's view the span tree domain for VLAN 10. Okay, and as I explained earlier, that the path from server 1 to server 2 is going through port channel 13 up to DCC1, which is also acting as the root port. That's reflected here, and for the root ID, that's also reflected here for the port, which says port channel 13. So the port connected over to DC2 through port channel 23 right here is acting as a alternative port, which is the backup root port on this switch. So when we create a failure, port channel 23 will become the new root port, and all traffic will be switched through that port within milliseconds. So when we view the MAC table this time on this switch, and let's reference only server 2, and do a pipe, include 4121, okay? Here you will see that MAC address is off of port channel 13, which is how we are communicating with that server now. Again, that makes sense because port channel 13 is the root port and in a forwarding state. Let's now create a failure on this switch, and we'll do that by shutting down the port channel 13 interface. Go ahead and type in shutdown. Okay, and now that interface is down between this switch and DCC1. Let's go back to server 1, and now we see that our continuous ping is still running as our network has already quickly reconverged after the failure because of rapid span tree. Fantastic. So let's go back to our access switch again. And let's go ahead and view the MAC table again. Okay, so now we see that the server 2's MAC address right here is off of port channel 23, which is connected up to DCC2 that we just talked about. And let's view the span tree domain for VLAN 10 again. Let's go back to that command. Here it is. Okay, and there you see that port channel 23 is now the new root port and in a forwarding state. Now port channel 13 is no longer listed because it is down. Let's go ahead and re-enable port channel 13 again on our switch to get things back up again operationally. Let's type in no shutdown this time. Okay, great. Now let's go ahead and view the span tree domain again for VLAN 10. Let's go back to our previous command. Okay, nothing has been updated yet. Let's go ahead and try it again. Okay, so now we see port channel 13 right here has returned as our root port and in a forwarding state. Therefore, port channel 23 is back as our alternative backup root port. Let's view the MAC table again. Go back to that previous command. Here we are. And there we can see that we are communicating with server 2, or communication with server 2 is going through port channel 13 once more. Let's confirm if our ping is still running based on these results. It should still be running, but that's always important to do that. And we do see communication is running as normal. So that is how using rapid span tree can provide fast convergence to our data center topology if there is a failure.